What we are going to do now is move our attention towards dynamic memory allocation and some of the weird stuff or some of the errors or catastrophic stuff that can originate because of how we handle the dynamic memory, right? And so, in terms of handling the dynamic memory, let's talk about the heap first, and then as a result of heap, we kind of come over and talk about APIs like malloc and free. So, what is heap? Let's take a look at that first. So what happens is you will take, well, obviously this is our memory, our beautiful memory going from 0x0 upwards, in increasing fashion downwards. And then what happens is every time on an operating system, so this is specific to operating system, and I'm saying operating system because in a bare metal system, you may not have heap management system, right? You may not have a library that has, heap related functions, so to speak. All right, so an operating system is kind of necessary, and this can be, the HLOS, high level operating system like Linux, Windows, Mac. So it can be those operating systems, or it can be RTOS, right? So RTOS kind of provides you with different implementation of the heap. Sometimes they'll like kind of provide static allocation, but let's not go into that. The idea is that you should have a heap implementation, right? And what implementation means is that there be some library or APIs that are provided to you, the developer, to essentially dynamically on the runtime request for some memory and then return back that memory, right? Okay, so how do we imagine the heap to be? So heap is, some pool of memory, right? So let's say, mm, for example, 10 MB worth of memory. Could be 1 GB, right? But let's assume 10 MB. Now the question is, out of this 10 MB, chunks can be like different sizes can be requested to be reserved for some part of the program. And so the heap management system is supposed to kind of keep a track of, which parts of the memory are kind of, provided to which, or rather, which part of the memory are already allocated to someone, meaning some function or some process, um, and which part of the memory are like free, and only within the bounds of the 10 MB, right? Okay, so with respect to this, then we have two APIs which are called malloc, memory allocate, and free. So the idea is that when we essentially call malloc, we provide bytes, like the amount of bytes or number of bytes needed, right? In terms of, okay, go ahead and reserve 4 bytes, right? Somewhere. And the heap allocator or the heap APIs or the mechanism of heap management, that is kind of free to allocate memory anywhere in that 10 MB that the heap allocator sees fit for management, right? And all of that heap management algorithm is hidden from us, in terms of like it's a library and you just consume it. Of course, we can go and see the implementation in the Linux source code or the FreeRTOS source code, for example. Um, but the point is that the APIs are given, you request a number of bytes required, and what the malloc does is the malloc returns a pointer. Right? And that pointer is, let's say, pointing to that memory location where the consumable bytes are available. Okay. And once, let's say, we are done using this memory region, what we are supposed to do is we are supposed to call the free API and provide the pointer here, right? Okay. So provide the pointer here. So somehow using the pointer, the heap management system understands that it is supposed to reclaim this memory, these many bytes. It'll figure out how many bytes, um, based on a management system. And then the idea is that next time somebody calls malloc again, chances are, let's say if somebody asks malloc, let's say 8 bytes, so chances are this much memory region would be given to them, and this memory here, which was previously allocated and later freed, um, can also be part of the new allocation. It can be reused. That's the whole point. And given that this 10 MB is limited across the lifespan of the program, we would want to use the memory when required and return it back to the heap allocator, or not heap allocator but the memory allocator, and just so that later on some other part of the program can use it. Okay, hopefully if this much is clear, let me get this out of the way and introduce the APIs. So so this is like the man page which I've found online, and this is essentially how we go about including the memory management related APIs. So we are supposed to do hash include uh, std lib.h, and once we do this we get access to these APIs, right? And forget about all of these, but if you notice here, malloc is the one that returns a pointer here, a void pointer again, and free is the one that takes in a void pointer. Forget, ignore this for now. That is just some fancy way of declaring a pointer, void pointer, but it takes in a pointer and it will go ahead and free the memory. Well, malloc takes in size and returns you a pointer. Now, what happens if malloc fails? This is interesting, right? And we'll discuss about this in potentially the next video. But right now, do think on the fact that what happens if malloc fails? What if the size you asked for is not available in the heap? Our heap was 10 MB, and let's say you asked for 1 GB. Right? Obviously, 1 GB cannot be located here, so malloc will fail. And do think about what happens if malloc fails. Now let's take a look at an example of how to go about using these. So we have an example here which I already ran. Let me clear the screen. Oh, okay, nice. Right. So what we have here on screen is a simple program, and stdio.h as usual for printf. Right. Then we included this library, the stdlib.h, as a result of which we can use malloc and free. What you should notice here is I have an integer pointer. So, int star p. So somewhere in the memory there is p, right? And then I say, hey, give me 4 bytes from the heap. And let's say the heap was somewhere here. So, I got, let's just assume these are, okay, let's assume this is 4 bytes somewhere here. Remember, we talked about this being a byte. So 4 bytes, right? So somewhere, let's say, I'm provided this address, hex, I don't know, DEF, well, DEC, right? So hex DEC is provided, and it was a void pointer. So it was just an address to the memory. So now what I go ahead and do here, which is strictly speaking not necessary, but I'm still doing it. I say that, hey, whatever this address that we got, hex DEC, um, hex DEC, please consider that to be pointing to an integer, meaning I'm enforcing that it is pointing to an integer just because I have an integer pointer here, and then say, hey, put this DEC value here, right? Now, if you see, P is pointing to this memory region, which is managed by the heap related APIs, and I got it through malloc. Right? Okay. Now what I'm doing here is just going and dereferencing these 4 bytes and trying to print those. Later what I do is go ahead, dereference this memory location, and when I'm dereferencing, because P is an integer type of pointer, um, dereferencing would lead to me seeing, or the code seeing, 4 bytes of memory here, which also matches with this, right? Okay. And then after that, I'm printing the value again, and this is equivalent to doing some work. let's just say, some work with the memory. So I'm like writing a value there, then printing it, so on and so forth. Okay. At this point, whatever value is available here, random bits, those would be printed, right? And later on here, 4 should be printed. Okay. And at this point, what I'm saying is, hey, heap allocator or hey, memory allocator, please take this pointer back, the P pointer, right? With please take this value hex DEC, and you had allocated this much memory to me. Figure out how much memory you allocated to me, and please also reclaim it. Please free it. I'm not going to use it anymore. This is like the agreement. When we do free, we say, hey, go ahead and reclaim this space and later on reuse it. Okay, so that was malloc. This is free. Let's go ahead and run this program. Um, and if we compile and run this program, we see at this point, well, it's 0, can be some other number for you. The idea is that here there would be garbage value, happens to be 0, and here you see free. Well, here you see 4 being printed, and after which we are freeing it. All right. Now at this point, let's just experiment what happens if you ask for 400 bytes, right? So how will this look? So we have memory somewhere, there is P, there is heap somewhere, and this is like a long, like many bytes of array. So let me maybe, specify that by having like a wiggly line here, wiggly line here. Okay. So now we are saying if we don't want 4 bytes, we actually want 400 bytes. So it will actually attempt, and if that much memory is available, which it should be, it will provide us with 400 bytes, right? But then see what we are doing. We are saying, hey, P is pointing to this, and P is of the type int star. So what I want you to focus on, and this is just like a bonus thing at this point, which is when you do star P here, yes, we are given 400 bytes, but we are only going to look at the first 4 bytes, first 4 bytes at this point. And why are we going to look at the first 4 bytes? It's because we are dereferencing an integer pointer, and an integer pointer, the machine understands that we are only supposed to consume 4 bytes. That's all. Mm. So, so the number 4 would be written here within the first 4 bytes, and rest are untouched, right? That's the point. And then at this point, when we do free, it'll go ahead and free the 400 bytes, right? So that's the idea. I just wanted to kind of emphasize on the fact that even though initially we were like allocating 4 bytes, that 4 was just because I knew integer is 4 bytes. But if you ask for more, you will get that much space if malloc doesn't fail. If malloc has that much space to, give you, it will give you that. But if it fails, some more funny stuff happens.